convinced. 4-1.
Yeah.
Yeah.
Yeah, I mean, hopefully he'll still join.
Yeah, so you say it'd be a four.
Just pretend he's thinking, something, I don't know.
So for
To me, like,
Did you send a note to him?
yes, I email Igor and Nathan to get same time. So
yeah.
yeah,
Okay, why don't you go ahead and start recording?
yeah, already started this recording.
Oh, really?
Yeah, I just started. Yeah, it's recording. I think now, right?
Seems to be,
Is that what that little blinky thing means?
I think so.
yeah.
Yeah, it should be means it's recording. I don't know where they will say, but probably they are recording right now.
Well, you have a pause button, right? So that probably means it is recording. Otherwise, there would not be a
Oh
pause.
yeah, the pause button. Yes. Yeah, we're recording, but let me just email Nathan separately. Just remind him.
Police.
Yeah.
Hopefully he's not in some kind of
lost.
I just looked up what his last note said.
Yeah, he said last time.
But why don't we get started?
I think they're finished, you know.
Check in a few minutes again.
Yes, they're not sure how stable his internet connection will be in the hotel. I'll do his best.
He says, I'll do my best. If you were able to record the session, I'll review it afterwards. I think it's go ahead and get started.
Okay, let's go ahead. Just pretend he's started.
Okay, so this is Qiaochu Wan's final defense. His title is right there. And I think that's good enough to get started.
Yeah, sure. Yeah, this is my title of the presentation of the bottleneck cell in 2D materials. We'll start with our introduction with some basic knowledge of the 2D material itself. Now we're talking about the 4 projects that get involved, including the wide area sample transfer on the recoupling samples, and also the exon platinum laser, and also the quaternions, our doubly charged bottleneck state. And the last one is the recent one, the trial motion we measured for the monolayer on the E-plane field. So let's get started with the introduction of the 2D material itself, and how the symmetry and how the PL will work according to the band structure and everything. So this is basically the family of 2D materials. So the very big family, big zoom. But you can see the mouse. So we have a conductor, which is graphene. We also have the insulator, which is HBM. We also have a semiconductor, which is a TMD, main focus here. They are different by elements, but they have one thing share in common because they can be exploded into a single model made by almost single atoms. In our case, the TMD main focus is the full name transmetal dicoconite. Is made by of the transmetal here and the coconite elements here. And the average size after acceleration is roughly 3.2 angstrom for which model it is. So for all kinds of 2D materials, they have a very different band gap, all the way from the conductor zero band gap, or to semiconductor band gap, also to insulating band gap. Those 3 are equivalent to nowadays kind of industry for silicon oxide, silicon, and doped silicon. So basically, we can use those as a building block with our MOSFETs, but in 2D materials. So this is our main focus, the transmetal dicogonite. It's the structure of this is made by have 2 kind of the crystal structures. The 2H1 is the most likely one we have, and the average layer, its separation is like 6 angstroms, and with also 3.2 angstrom for each layers. All the different TMDs with different combination of the transmetal and coconut atoms would have very different band gap. And the one we are choosing right now is MOSC2 because of the very clear spectral properties for us to identify all the particles inside. So the reason why we are focused on those kind of material is because of the symmetry tells us why this is a very good material. Firstly, we know the symmetry have C3 symmetry because it can rotate here 120 degrees. They also have a symmetry in the planes and also have C2 symmetry along those three axes, which give us a D3H axis, D3H group in the gamma points. While we move to the K points, we are losing the C2 symmetry or sigma B symmetry because they are mapping our K1 point to K prime point. So we are focusing on K point for C3H symmetry because the K point is we have the direct band gap. So the band gap is very interesting. We know our materials are made by the transversal atoms and diagonal atoms. If this set alone, one monolayers, they will become a direct band gap. This is the semiconductors with their lowest band gap here is at K points. If you stack them together, the p orbit of the AC atoms will interface, reducing the the Q points at the band structure and increasing the gamma points, the gamma points. Those will result in you have an indirect emission if you have multi-layers. So the good thing is I can tell it very differently from monolayer to bulk, even by bilayers, because the emission is very different. And you can calculate the band structure based on the d orbits of the MO atoms. That's what we have. The interest you must notice that at K point and gamma point, the contribution of the orbits are very different. At K points, you will have the dz square mostly contributing for the conducting band, and dxy my square plus minus dxy contributing for valence band. While in the gamma points, it's on the otherwise, it's the dz square contributing for conducting band, while dx square minus y square plus minus dxy contributing for the valence band. And also with those d orbits, they have coupling with spin of the electrons. They will have a very strong spin orbit couplings. So we have a splitting for both valence band and conducting band, which is true for all kinds of TMDs. But once you mention that for different kinds of transmetal you are using, the order of this can be shifted. For example, for the MOSC2s that we care about most, the closer band are all spin up, while this is a spin down. So the splitting are very different, also very different from the different materials. This is generally the case we are using. They always have bigger splitting on the valence band and less splitting on the conducting band because it's gamma 1 here for the valence band when we go to the band with the group theory. So what's the usage of such a direct band semiconductor as a monolayer? The direct application would be, say, okay, we have a semiconductor, exciton is the most easy particle we can observe in semiconductors. For 3D case, the 3D excitons will have a 3D distribution of the detectable state. So the binding energy is reduced. But if you go to 2D, because of the 2D nature, the detectable state gives you a bigger binding energy. And also, because we are 2D, the electric field can go up and go beyond the sample. So it can be strongly screened by the media up and down. So that gives us another way to tune it. Usually we'll use HBN, which have a higher index, so to make it more stable. And must mention that for the spin structures, as calling about the spin structures, so because of the Fermi-Golden rules combined, we will have two kind of excitons. One is A excitons, one is B excitons. And because of the coupling for spin valley couplings, you will have a K valley correspond to the gamma plus, and the K prime valley for gamma minus, which will be important in the future when talking about the spin state of the quaternions. The exciton A is mostly our focus. Most of our research are focused on the A excitons. And also you mentioned that along the intralayer exciton, means whole electron in the same layers, it is also possible to have excitons across the layers with one electron in one layer and a hole in another layers. Those kind of interlayer excitons usually have much longer lifetime. And along for excitons, also have other excitonic states, including trion, which is the exciton attached to actual charge, or bi-exciton, two exciton, two dipole, they connect together. And even more, if you consider much other complexes, can be over 5 particle, even 6 particle states. So we have a big zoom of all the excitonic states in our 3D materials. Then how do we identify which state are we observing? Then introduce our optical setup, which we offered by Johnny to start this dual image resistance. So while we're pumping with the laser of 532s, and then we go from the beam splitter, go to samples, and then we step back and go to spectrometers. They will tell us the photon energy, and CD will report the density. While we also have another light path made by white lights, they will also image on sample but go back. And here, image on CHD camera, so we can know where we are looking at. Because our samples are usually pretty small, unlike the gamma samples, they're pretty big, but very small. So it's very important to know where they sit. So what it looks like here in the CHD cameras, we are looking at something called photoluminescence. We are exciting those excitonic states with high carrier, we go to high energy, let's get relaxing down and emit light. Here is an example of the WAC2 photoluminescence, while the y-axis is the backgate, the x-axis is the photon energy we absorb by spectrometers. And this is also an examination of what it looks like for different layers. So I can tell one small layer by layer very distinguishedly. So you can tell the small layer or bilayer very distinguishedly. So you can interact for bilayer. So the PO emission drops dramatically. So here,
Just go back. What is the X1 and X2 minus?
oh, this is for the ABX. It's a AX, A trial and B trial. This is for WS2.
Okay.
So this is now what can we use for the excitons? So one of the direct applications is a boson. Can we condense it? And the truth is, yes, we can, but it's a very heavy mass. So we invent a trick to make it easier to condense. So firstly, what we need is this is a distributed drug reflector, basically a mirror. And those mirrors are reflecting light very high index at a certain wavelength, we call it stop band. When you integrate two of them together, you have a cavity. And with cavity, the photon can trap inside and actually have some tiny bit effective mass. The effective mass E2 minus 5 MeV, very tiny, but that's enough for them to have interaction with the exciton we have inside. So when you put RTMD inside the cavities, you have the exciton coupled with the photon mode between the cavity. Here, if you write in this way, the x-axis is the momentum space, which corresponds to the angle of emission of light, also corresponds to momentum in plane. The y-axis is the exciton or the photon energy. So you can see that this flat line is the emission of their excitons. It shows a flat line means they have no preference in the momentum space, or say they have no preference in the angles. While the cavity here, because of the solid by transfer matrix, can tell they have proper distributions for the dispersions. When they are intersect here, which is called resonance, they'll open a gap and split out to be upper and lower polaritons. So basically, you are solving this two matrix, and you are having two branches made by upper and lower. So the advantage of doing this is that because we use the best of both excitons and also photons. Photons are purely linear, so you have not have strong interactions. Excitons do have a strong interaction, but you have very heavy mass. So we combine those two, we have both a small mass, but while still have very strong interactions. So that's why we split them. And also, the light mass means that we have a high TC because of the TC formula is proportional to the 1 over the total mass. So when you use exciton polaritons, will make the system easier to condense. In condensing a higher temperature or lower density. So then how do we combine with TMD? So for gallium arsenide, it actually should be simple because we are growing DBRs and we're growing the gallium arsenide on top of it. In our case, sadly, you grow TMD on DBRs because we have one of monolayers. Any defect in monolayer is we have very strong trap in your excitons and also will destroy your photoluminescence. So it's why we usually use the method to grow bulk first, exfoliate the bulk, and stack them. That also leading the result that we also need to have a top DPR without being growing. If you grow on the TMD, also destroy TMD, we invent a new method to synchronize top DPR on DPR with our TMD, and whether or not can make it in a bigger size, almost similar size to gallium arsenide. So to do that, we need a wide area TMD monolayer and a wide area DBR cavities. This brings out my first project, so you're creating a wide area 2D materials for weakly convex polaritons. Firstly, we start the bottom DBR, which is simple, which is a silicon oxide silicon nitride DBRs. And the top DBR, which is something unique, we don't use in the growing top DBR. We're using a transferable DBR made by the Forest group. So the trick here is that a zinc sulfide has a very big lattice mismatch with silicon on substrates. So they're easy to peel off by the PDMS. So while it peel over PDMS, they stack them on top of the other DBRs. So now we have two DBRs. How do you get a model between them? So there are multiple methods for TFT installations. The scorch tape method is more traditional ones, even to the graphene 2004. They also have the liquid method, which give you a slightly bigger, but the less in qualities. Also have the metal exfoliations, which we're using now. This is this project, and also the CVD ones, which is big, but the quality is much less compared to the scorch tape and metal exfoliation. So this is how this was done by the tape exfoliations. You are using the tape and you attach them to the bulk and you kind of peel it off. You can put it on a substrate either to the silicon oxide or to PDMS. And while you peel it off, you leave off those things you can observe on the microscope. You can either tell by experience or like we have our undergrad help us with our CVD calculator machines to tell whether or not they are monolayers or what's the thickness of HBN in this case.
Was there a question there?
Any questions?
Right.
Yeah, so, and while we have monolayers, now you stack them, right? So stacking is a tricky thing when you build our transfer stage, and we build one by hand. You basically line by your eyes on the microscope and by hand. One of the reasons why we must stack them, because HBN encapsulation can largely increase the property of the monolayers because the monolayer have no restriction on the axis. Well, two reasons. Firstly, the high index of the reflection, allowing them to be a very stable excitons, and also they're controlling the z-axis phonons. They all increasing the exciton lifetimes. So this one typically look like after you stacking. So while you're looking at the gold one is backgates, this blue one in the back is the bottom HBNs. This yellowish one is MOSC2, and the big one is the top HBN. So basically, you encapsulate them inside, so they'll be safe and away from the harm from the outside world. And this is what it looks like if you use the liquid method. This is the way we work with the Shubei and it's not the same use. They can give you a much higher, a bigger size, 40 micrometers, and the quality is reasonable. And we try to put it between our cavity. So this, the blue one, you're looking at bottom DBRs. The red one, the top DBR by transfer method. This, in this blue in here, is the MOSC2 encapsulated by the HBN inside. And what do we observe? We do observe some kind of splitting. Well, first we mentioned we have two kind of parabola because the surface is not very flat. We kind of have two cavity mode, but the axon coupling is one of them. And we can see the splitting. We zoom in here. You can see this is the bare axon photon, bare cavity photon, and also bare axon are coupled here. And the split in the gap here becomes lower and higher polaritons. It's a very small splitting, only 10 MeV, so we are still in weak region. But it put our message that the transferable DPR works. So now we still have a very small TMDs. Can we make it any bigger? As I mentioned, we try the liquid method is very big. We try the same TMD, say the growing direct growth, give us a good quality. So the why we try this is called the gold exfoliation method. It can give very big and very, very nice. So the way to make it work, you need to make something called gold tape. You need the gold deposit on the thermal tapes because the manner forces between the gold atom and MOSC2 are almost as strong as the in-plane manner forces. So you can almost peel off exactly one monolayer off the box, and then you transfer on the substrates. They be very big, be a few hundred micrometers, even millimeter size. But there's a problem. If you just put it on the DBRs without any encapsulation, like HBNs or any other isolations, the quality is really bad. So this is what you are looking at if you only have monolayer transfer on DBRs without any encapsulations. Those big chunk of blue is actually the excitons. Because of lifetime is so short, you have such a very big line width here. While this parabola is the cavity mode. So you basically not have very strong coupling, or you say even no coupling at all. This probably because the enhancement of cavity mode itself. this was a look-like sample. The good thing is very big because everything you're looking at all monolith. So this all monolith covering the whole bottom DBRs. So you just transfer the top DBR on it. Basically, hit the whole area. We are looking at the whole the 1 millimeter size of TMD encapsulated inside the DBRs. But still, quality is not very good because we have no encapsulations. How can I solve it? So because HBN is very tricky to transfer at that time, actually, now they have a different method that time work with. HBN is hard to transfer within one area. So with Sweden step, we even method called the dodecanol encapsulations. So instead of HBNs, those thing called dodecanol, basically is the organic molecule with 10 carbons. We will first polish our silicon oxide, which is hyperbolic. So those molecules can sit vertically like a spring. So then you do wide transfer molecule and make them like between the spring. So those springs can suppress its oscillation interactions. And also, if they have any vacancy here, they can also reduce the vacancy here. So as you see, if you compare the PL for bare without any encapsulations with the dodecanol encapsulation or HBN encapsulations, can surely tell, yes, we have huge enhancement on dodecanol encapsulations, but still not as good as the HBN encapsulations.
Go back for a second. Are those relative intensities?
Yes.
Meaningful?
Meaningful.
So it really is brighter for the HBM.
Yes. Yes. Especially we measured on the similar model that we have for the company. And with dodecanol, we believe we do see some kind of coupling. This is what look like after you have this. It's the whole area is covered by dodecanol, monolayer, and dodecanol, but you can't really tell because it's kind of a whole area. We believe we may probably see some kind of splitting. And the reason why you can notice the exciton has become much narrower because of this effect, the quench, the reduced in-gap emission, and also reduce the phonon from the dodecanols. And also, if they compare, but sadly, due to power series, it's still pretty linear. So this is what comparing the dodecanol molecules with HV encapsulated molecules inside the cavity. This data we're doing with the sonation for upper branch condensations can tell dramatic differences. For our wide area dodecanol encapsulated molecule, if you look at power series, still pretty linear. It's a very, very weak couple. And while in the sonic samples, you can see they have very strong nonlinear regime above the superlinear regime here. So although we do manage to make a weak coupling exon polarizon on a very large size by the dodecanol encapsulation, but we still don't have a very strong coupling. We still don't have a condensations or any lasering. This is a summary of what we have done with little projects. So we observe a weak coupling exon polarizons for small size, proving the transfer property works. Then we exfoliate the white area samples using gold exfoliations without encapsulations. It's getting very bad, and also no couplings. By introducing dodecanol encapsulations, we increase the qualities, and we believe we have some kind of weak coupling in the white areas, but still not strong enough to see any nonlinearities inside samples. But can we see any linearity inside the exon polarizon for 2D material? The answer is yes. And we do it in a very different method. We're using HBN. The second my project too. So
before you go on, let's give them a chance.
Oh yeah, sure. Forget the issue. If any questions for this project.
Questions before it goes on to the next section.
I want a naive question. Why does a nonlinearity indicate strong coupling?
Oh, so actually the strong coupling is not have multiple criteria for this. Either by Rabi splitting, if you see the splitting larger than the line width of this, they
So
can
here you would say the splitting is comparable to line.
yes, but if you looking at the nonlinearity, means this is pretty linear. That means you have little interaction, no exon level interaction inside of it. It's pretty photonic, mostly the photons. That means the encapsulation of the exon is pretty weak. Another criteria is the blue shift. I don't show here, but we only see red shift causing by the phonon, but no blue shifts causing by the interaction with the exon polarizons. But this is just showing a comparison, say, with similar sample with the dodecanol encapsulation and HBN encapsulations, we can surely say definitely no swinging region. Basically, it's a very weakly coupled, mostly photonic.
So actually, what are the x-axis?
Oh yes, so x-axis is the pump power we inject into systems. They are both our pump powers. The y-axis is intensity of the PLs. If our sample is an exon polariton, extron coupling, you will not only not see just only a linear regime by photons, you also have interaction from the exon components. Because photons are pretty linear, they don't interact with each other, very hard to interact with each other. But if they couple with exons, we tell each other, they will have a linear regime. But we don't see such things.
So this is kind of busy, but you should compare to the blue curve.
To the blue curve.
The blue curve has a nonlinear jump at the lasing threshold.
Yes.
That's coming from interactions.
Well, I mean, you will still get lasing if you go to really high power. But
For
the
the-
idea is to
for
use
the-
the interactions to reduce that threshold.
Oh,
And there's no threshold seen there, it's just linear all the way up. So presumably if you kept pumping hard enough, eventually it would become a laser.
Yes, I mentioned on next project, how it's different, the photon laser to exon pattern laser. So if you go pump very high enough, you eventually see a particle inversion and you eventually become a laser. But you pump very high enough.
Or you burn up the
You
same.
burn a sample. Most likely in our case, you burn a sample.
okay.
So I know it's not the goal of this project and it probably would kill your sample, but did you happen to try throwing this thing in a cryostat and seeing if you could get it to make a condensate or get?
This is already past that.
Oh, it's okay.
It's for Calvin. We be together. But...
Oh.
Yes, it is.
Of course we did.
Double checking, like the yellow line from the busy plot, is that like the same thing as the linear line?
Yes, linear line, yes.
Well, the powers on the x-axis though are quite different if you measure higher.
Oh, yeah, the power is different because this one's mu watt, it's different units. Units is different.
Okay.
So the one on the right is not our data.
Yes, it's Sonic data, because it looks better, because it compares.
Is that Sunny's data? Yeah.
Because the reason why we should all data, because shows stem for DBR, we do, so this is more comparable. This one has exactly stem HP DBR, it's only difference is that it's HB calculation, but into decline position.
So the bottom line is the decane is better than nothing.
Yeah, but still not good.
It's third is good as HBM.
Yeah, that's our push this for this. So we eventually switch back to HBM. Any other questions? Okay, so let's continue with our HBM calculation. So now we say the back doesn't work, must stick with HBMs. So can our HBM calculation because anything usage? They were talking about polariton laser, as I mentioned before, they have laser thresholds. Actually, they have two laser thresholds. Why?
So this is HBM encapsulation, but not wide area.
Yes, this is for WSC2 condition. Two things we do differently. Firstly, we use HBM. Secondly, we have triple. So we use triple quantum well. By triple means we have 3 layers of monolayers. It's a common trick people use for gallium arsenide by increasing its the density, increasing the all-section strength. So you have multiple layers inside of here, separate with the similar thickness of HBM. So you are increasing the density at that area per area. So they increase also in strength. So what we are observing here is that we actually the same structure, it's just we're using the HBM and the WS2 instead. So the what we're seeing here is called the polariton laser. So what is polariton laser? The laser have two thresholds in our case. First threshold is firstly when you have the BC laser, which means you're pumping very just actually ground state exciton and couple with photons at almost a ground state. So when they condense, they'll become coherent. And the light coming out of this coherence will also carry the same information. So the light is more coherent. They have coherent emission, which we call it laser. But if you pump hard enough, you'll eventually make enough of exciton into the valence band. They'll become like this shape, and you'll jump down, but still make emissions. So these are also coherent. So if you draw in this way, and you see I have the two dominant regions. One region is created by the interaction here for the BC of the exon polaritons. The second interaction region is caused by the particle inversion of the photon or the excitons. So we'll be focused on this region because this is allowing us to have a laser in a much lower threshold. So this is how we make our samples. We're stacking 3 layer WS2 between and together and spacing by HBMs. Can tell the typically PO looks very typical, and we are recently trying to make cavity recent with our exciton, not the trion. So this is what we look like direct by bare eyes. So if you look at the sample just by our eye, you will see a red color here. Why? Because of emission of the laser is not at the same wavelength as our laser pumping. While pumping with green laser 532, but you look by eye, the sample is shining a very strong red light, about 800 nanometers, exactly the energy of axion flaretons. And how do we know this light is not a PL, but the laser? We do interferometries. It do show the different patterns that may us know, yes, we are looking at some coherent emissions from the sample. And what does it look like for the photoluminescence? So here is the K-space photoluminescence with x-axis to be the angle, which corresponds to the momentum space, and the y to be the energies. And what we can notice that we have very bright spots at very high angle, not at k equals zeros. And this is because of the lifetime is short, so you don't have enough time to relax all the way down to k equals 0 and emit it out. It's actually pretty common for most semiconducting lasers. If the lifetime period is not long enough, you will have emitting happens in a higher angles. So how do we know we have lower threshold? As I mentioned before, we can do a similar thing by pumping power, changing the pump powers and the photon countings. You can see there's a long linear region here. And also, if you keep tracking of the emission line widths, you can see the line width drops dramatically at a similar area. So this regime for pump power is our threshold, which is 98 nanowatt per meter squared, which is pretty low for most semiconducting lasers. And we can also solve, we can explain why for this long region just by the calculation for the laser rate equations, with the generating for G, and N is reservoir, which is a hot carrier created by pump lasers. The tau is the lifetime of the reservoir. A is the interaction term between reservoir and the polariton, and TSP is the polariton lifetimes. So we can solve this equation and can fit it, can give a reasonably good fit, explaining why we are looking at such a nonlinear region here. And if we're looking at the efficiencies, the efficiency here is roughly 3.82%. It's because of this by counting the laser get inside, the laser out over the laser get inside. So this is not as high as the electron injection. So reason because we have a top DPR on top of it. When the laser shine inside, we'll lose a lot of the laser by getting inside the top DPRs. So if we choose an electron injection, but direct injection of electron holes, it will be much higher in efficiencies. So by conclusion is what we did. We see this axion electron lasering in WS2, and we're proving the very low threshold and reasonably high efficiency, considering we're pumping with laser, not the electron injections. And also, we think it's very helpful for new on-chip coherent light source called VCSELs, because they're vertical cavity emitters. Any question for this part?
So the data that you gather, would you say then that it kind of proves that you have a BEC?
Yes, this nonlinearity shows that we have BEC
So
constitution.
there's no other explanation for it.
I guess we call it a highly non-equilibrium.
Highly non-equilibrium constitutions.
Yeah.
So the stimulated scattering matters, but it's not very well-defined temperature. It's pretty out of equilibrium.
We are all equilibrium in this case. So even though the sample is measuring low temperature, but the temperature of axion polariton will be higher than the base temperature.
So if we look up there, go back up there, the top left equations has a down conversion factor that's proportional to the number of photons. The end pole.
The end pole, yeah, I mean,
Yeah, that number right there is
the end pole.
that's basically a stimulated scattering.
Similar scattering.
And so that implies macroscopic occupation of the flaretons.
Yeah.
But it says nothing about whether it's a good condensate. It just
Right.
says they have high occupation.
Right.
So that's as good as you can say.
Yes.
Okay.
The
So-
very long
so-
equilibrium.
So we cannot.
Can I ask a quick question?
Go
Can I-
ahead.
Oh, well, question from Igor.
Yeah, just a previous slide, please.
Which slides?
Yeah, this one, right panel. Why do you have this efficiency drop with pump power? If
Oh,
you could-
this is when we measure efficiency before and after the threshold. This is commonly called slope efficiencies. You will not. This drop is caused by the thermal the phonon scattering. The phonon, you are getting hotter and hotter before they go to the threshold. So you can have reduce of this efficiency of the photon scattering.
I see.
If this are
And then it starts generating.
it's also going down slowly.
And then
because
it starts-
scattering.
Okay, okay, thanks.
Did you have?
So, sorry, to finish up what I had, so, you cannot infer anything about the coherence of the polariton states, basically.
We have a-
You can only say there's a population of polaritons, they contribute to the lasing.
We have the boundaries, so it
So you have interference right there.
is coherent.
Yeah, okay, from that then.
Yeah, so it is coherent. So we can still call it laser. It's a
Okay.
bad laser, but still laser nevertheless.
So basically, there's lasing and there's condensation, and
Right.
they're on the continuum. And this is sort of on the interacting
But, okay, let
side.
him up.
Yeah. So,
Yeah, this is why I showed you here first. That's a key evidence is
so,
laser.
okay, so let me put it as a question. This could be a laser. What makes you say it's not merely a laser and that it's actually the interactions matter?
It's because of firstly, we don't have a very clear the coupling that since we are into very clear coupling regimes.
So the question is why it's not a laser? Why do you think it's not a weak coupling laser? Why do you think it's a strong coupling?
We are not in a we're in middle region, I would say. It's not a strong or weak. We are in rather call it the middle coupling regions.
Okay, so what data tells you that it's middle and not weak?
So firstly, by this, actually can tell you something. Is this because of this a strong emission here? It basically shows we have not happening on the cavity. If you are happening at a photon cavity, the photon laser, like fully made by photon or by exon polaritons, you'll be having a lower here. But here you see we are using an intersection of exciton and the photons. That means these have components of the exotonic. So that means the complete no coupling, we have some coupling here. And furthermore, if we look at the interference patterns, if we look at the lifetime, the lifetime here is actually in a reasonable range for the medium coupling exon polaritons. And furthermore, if you look at the drop of this line width, we have the drop of a line width. This drop of line width also shows this they are all due, they kind of scatter into a lower energy state. So we believe we are.
Well, you have line narrowing in the laser too.
Yeah, but in a particle inversion happened first. So we need to stay before particle inversion. So the things that happened before that, so we can call it the exon polaritone.
Well, the one that you showed before is probably the best evidence that it's happening where the exciton
The
is.
exon is, yes. So we did not happening at K zero. It's actually happening here to become a bad laser, but also proving it's not a normal photon laser, it's an exon polaritone laser, made by weak coupling, non-equilibrium condensation of Boston concentrations. Okay.
If you did this at low power, does it look like the nice classical coupling curve?
We have a very weak coupling.
I see, so it's hard to see.
It's hard to see.
Yeah.
We estimate roughly like 5 to 6 MeV. Okay. Any other questions? Before I continue?
So I think you said that like this is also one of the second or third best lowest threshold. laser.
Yeah, that number 59 nanowatts, that's pretty darn small.
Yeah, the second lowest.
Okay.
Can I ask one more question here?
Yeah,
Right
sure.
panel,
That's
right
fine.
here on the slide.
Yeah.
So you have line width as a function of power, and then it goes flat. I'm talking, and then it drops down to indicate that you start generating coherent emission, and then it raises.
Yes.
It broadens again. So
Yes,
my
yes.
question is about this last part. Why is it broadening? It's
the
higher
same
power.
reason for reducing the efficiency, the phonon, because getting hotter and hotter, you will have
Oh,
more
okay.
phonon scattering it, reducing the
I see.
lifetime, increasing the lightness.
I see. Okay, thank you.
That reason for why the efficiency drops.
Yeah, clear.
Okay. Another questions? If I continue?
Let's go on.
Okay, that was a big one. One of the big topic of my PhD thesis. But as we mentioned before, all the BC I introduced before, whether weak or strong, they're exon polaritons. They are boson, yes, but they carry near charge. Even if they can float, you have electron float, but carry no charge. So you cannot use it for any transport measurement. But think, is that possible? We have a boson in the flow like BC, but carry some charge. And the answer is true, we can. This idea is not new, it's from the old idea. It's from short course superconductors. This series proposed before the BC series. At that time, people think maybe the superconductor can be explained by charge boson condensations. Although it's kind of overthrown by the modern BC series, but we believe it's still valid in our case. We can make it work. So how to make it work? So the trick is to build a system like this, made by two bilayer systems, bilayer TMDs. You have one layer, have something called triangle before, an exciton attached to a charge, and another actual charge on the top layers. So the overall, you have 4 particles, which is an even number, making it a boson, while the total charge counted, we have +1 in one layer and +1 in other layers. You have +2 for total. But for first glimpse, you see this sounds stable because model layer 1 is plus, the 2 is plus, it will repel each other. The trick is we have the metal underneath. The image charge created by metal or say plasma screening reduce repulsive and make it more stable. So by building it, we are building this TMD and put it close to the metals. So the D and L, which is the second HBN, become very vital importance here. So how do you prove the metal is helping? The metal indeed helping, but control experiment. So firstly, if they compare the same stack with or without metal, you will see this Q line only appear when you have metal, while this appears without metals. And also, if you're changing the distance of D, which is the distance between the metal and our stack, the quotidian will move with it. As we explained, the quotidian is introduced by the screening, so that will affect it. And also, we also see it's in a different material, WC2, we also see it. So it's not like unique for one 2D materials, but you can see other TMD as well. And they can all even survive at a very high temperature, all the way to 60 Kelvin, give us some hope, say it can be a high temperature superconductor. So this is temperature dependence showing for different WC2 and for metal and without metal, you can see the clear differences. This one can survive nearly 60 Kelvin. So the energy of the quaternion and triangles are very interesting. This is a theory done by Professor Bondrov. So we are measuring, we are calculating the recombination energy of the quaternions. That means the emission we see by our CCD cameras. I remind you, the CCD camera, the photon is not carrying the full energy of the system. It actually any differences between the starting state and the end state. So the difference between trion and quaternion in the PL do not correspond to their actual binding energy inside the sample. So here you can see at different thickness, they can be overthrown. One can be higher, one can be lower, which you do observe earlier that quaternion and trions can swap their positions in our PL spectrum. But again, does not mean their binding energy is also swapped at this case, because the photon energy is different from the binding energy itself. Then, how do we prove that that line is belong to the quaternions? So we do 2 acid tests for that line, whether or not that belongs to quaternion. First one is we do the electrical measurement by contacting with 3 gates. One is the back gate, here the middle gate, grounded, and the top gate. By doing this, we try to control the doping level for each layer separately. Also the trick here to make sure we can stack everything here with this gold gate that we're using a method called the bilayer photoresist. So we sprinkle 2-layer photoresist and then we do intercuts. So that gives us a very flat edge for back gate. So the molding will not break on the edge. And much more, almost very thin, only 1 atoms, only 0.7 nanometers. It's so thick to break. So we invent this method to make sure the extend molding outside our back gate, it will not break. And how do we tell whether mobile actually quaternion or interior excitons by tuning the gates? Here is the diagram, the phase diagram, what we can see. So firstly, the back gate is positive, which introducing a negative doping for the bottom layers. And while top gate is negative, introducing the negative charge, this we recall we have the negative quaternions. If you move down the line, we fix the top gate and change our back gates. Top gate still gives you negative dope, but back gate becomes positive dope. So you can see immediately the positive ions unstable with this charge. You can see there's a problem trapping here. If it's unstable, it will eventually become an interlayer trion or interlayer excitons. This is where we dream, we would expect to see the interlayer excitons. Vice versa is also where we see the other charge of interexciton, and this we see now we have a positive quaternion. So we can tell our structure different from the people who claiming for the interlayer excitons. Another thing is see we don't have a dipole inside of samples because they are sharing the same charge layers. When you plan the field across it, not a dipole, you will not have strongly shift with the PL. We'll see later. So firstly, when you're changing the baggage, you can see the quaternion going brighter and brighter comparable to the trions. If you think about that, you're doping more trions and quaternion extra charge, the quaternion getting brighter with trions. If you are tuning the top gates, you actually can see the two charge, the both negative charge and positive charge quaternions at two different ends of top gates. And how to explain that? Firstly, we're thinking about changing the baggage here. We are actually introducing more trion here. You can see at some region the trions are more than the quaternions, and they keep going. And you have the N domain, which have both negative dope, you will see quaternion become more than trions. It's an even stronger case to look at top doping, because at top doping, the trion on the bottom layer does not change, almost a flat line. But when you're introducing more and more doping from the top layers, you see quaternion increase dramatically compared to the trions, because they are trion attached a charge. The quaternion does not change much because we fix the doping on the bottom layers. And we can explain this just by a rate equation as we have for the laser. Basically, you are solving a three thing. One is exciton, one is trion and quaternions. The quaternion will get a charge from the exciton, and the trion get charge from the exciton, and quaternion get a charge from trions. Those equations can help us to calibrate the total doping densities by the ratio of the trion and exciton and of quaternion and trions. And also, how do we prove that quaternion is not a defect or a charge defect? By the power series, we're changing laser power and look at the density. The quaternion is most linear compared to the excitons, so it's not a bi-exciton or it's not a defect. You will see some of the behaviors when you go to higher energies. And the last one is that now we know quaternion is charged, and it is not a defect. Now, how do we know the full state and with exactly a Boston we said? So this is our major experiment we do with the macro-optic measurements by putting the samples in Florida. When they scan it with strong magnetic fields, and you can see that in strong magnetic fields, the energy of exciton, trion, background all shifting linearly mostly. But for quaternion, it seems to have a bending here. But actually, we show it's not actually a bending. Actually, you are seeing a mixing of two states. Because of the quaternion, we are making at the 1/2 of spin from the trions and 1/2 for the charge. The total spin is J equals 1. So you will have three branches, J equals 1, Mg equals 0, Mg minus 1, Mg plus 1. So this will give you three branches. And I mentioned before, I'm talking about the spin locking of the circular light with the valleys. So these are all examined by different circularization of light. This one is we put our right circular polarizer in front of the camera. This one is a left polarizer in front of the cameras. So you'll see something very differently. So first, if we follow the line, you can see first it won't go very linearly because we're observing this line, which is J equals J minus 1 here. It goes up here. And while it will go up to all intersection regions, because we're in the low temperatures, the Boltzmann distribution are going to occupy lower energy state. So when they go beyond this point, these two states become a lower energy state. So you will no longer see the extent as linear. You are occupied by those two states. However, as I mentioned before, we are measuring the right circular light. So we can't see this line, because this line emits light from the left circular light. But we can see half the middle state. Because the middle state, Mg equals 0, is unpolarized. So you can see half of it for both right-hand side or left-hand side polarizations. So you can see here, simply bending over here. So vice versa, it applies to when you look at the left circular light, when the light goes up like here, and they flatten out, simply flatten out, they actually occupy the lower state. And you can only see half of this state, but it becomes actually dimmer. So I can see this becomes a little bit dimmer compared to here. We can only cut by half. We're looking at a certain circular conditions. This is a simulation we did. We can see the simulation have very good match with our experiment data. So our theory can use to explain all them by the spin Hamiltonian series by Bondrov. So we can tell that with lower state, we can explain this by the spin Hamiltonians. Consider the triangles put together at a spin, total spin 1/2, and active class spin 1/2. They have their own linear shift, while they also have their coupling terms. There's A. This A is minus because they are attracted because of screening effects. And we can solve it for J equals 1. This is for the lowest triplet state. You will have the straight branches. You have the two linear one, and the one is a pretty straight line, but plus a slightly quadratic term, we can bend in a little bit. But we must mention this is all J equals 1. We also have a J equals 0 state, which we believe is a higher energy state. So we can't see here as not ground state. We're measuring in 4 Kelvin below temperatures. So only observing the lowest state of the system. So this is basically our found difference Q1. We know this Q1 exists for our binary systems. It only exists with metal. And we know by the doping experiment is charged. By the metal experiment, we know it's J equals 1 is a triplet state. So actually we're proposing we might seeing some kind of possible superconductor, not by BCS mediated by phonon, but rather mediated by exciton, or we can say photon-induced superconductivities in the structures. The moment you see it is that you can see those two electrons are attracted by this interlayer exciton here. So they can this kind of work in the same thing as the phonons. But difference is for phonons of normal BC series, the phonon density is very important. They have high pressure. They can't reach the low high temperature without high pressure, because that high pressure increases the phonon density. Like in our case, we are determined by the exciton density, or we should say that there's a trap or term densities, which you can tune by light. So with our light-induced without being the pressure, we can increase our light density, so pressure to push the TC to much higher, to potentially have a much higher TC superconductance. So this is
So just point out that diagram on the bottom right is not what we're proposing. It's a different diagram, but
yeah, it's
I'll come back to that. That would be the electrons sending a photon from one to the other and making an exciton in the middle. But you've got a pre-existing exciton.
yeah, it's hard to do it.
I can try to draw it up there maybe later, but let's stop and ask the questions again.
So I missed that, what of your data indicates that you do have a superconductor?
We don't have a superconducting. We have proving the charged photonic state.
Okay, so this is an outlook.
This outlook.
I see.
And we will show you we do have some progress for the transmission.
So could you explain again why you don't see the upper line, like the upper?
Yes, I always ask that. So because of the boson distribution, like we are at low temperature, they will occupy lower state. So you will say these are getting bright very deep.
So if it's occupying both the lower two states, why not this?
Actually, they are both occupying this state majority. Because if you look at it here, this corresponds to this state. And we can also some of light coming here. The mostly is this is the most occupied, but you can see it. Since we're looking at the right circular light, because they are those emissions have a dependence on value and circular radiations. So when you're looking at only the right-hand circular lights, you can't see the most occupied state. You can only see a blurred image of a lower second lowest energy here. This one is not porous. So you can see half of it here as a dim line here. So it's because you understand why I mentioned about the span structures, because they have a value dependence of all the emissions. So you pick the valley, each valley corresponds to different right circular light. So some lower state like can't see with one circular polarization.
That makes sense. Yeah.
So yeah, that's the real diagram for our case. You have a pre-existing exciton. All right, and then there's a Coulomb interaction of each electron with that pre-existing exciton. So you're not creating an exciton.
Because I think about the light coming in, you have exciton, you have one charge.
The photon comes in here, right? So you got a photon that comes in here, creates an exciton. Right.
Oh, yeah, okay. Oh my God. So actually, this should be, those should be the photon. I make wrong. This photon, those should be electrons. I think I make it wrong. I think I make it wrong. Those two like are electrons.
Yeah.
Those two are photons. I think I make I think six. For some reason. This one.
Well, it's still not quite the same, but
So
anyway, that's all.
No,
What we're saying is we know this exists in this way.
so you're not talking about the BEC of quaternia, something different.
All we're showing is that they exist.
Exist.
It's charging.
So you have to put it pre-carry, like we have pre-pair. When we see a pre-carry, but they're not condensate. It's like we have pre-pair for the high temperature conductors. We have pre-pairing electron, but they're not condensate.
So let me think about it. The electrons want to pair together because they can form a quaternion with the exciton.
Yes.
Okay.
So this is a pre-pairing, like a.
So it's like a three-point pair, basically. The electrons are sitting there tied together by the exciton.
The carbon-based high temperature conductor have pre-formed pairs. Yeah, because we this is a kind of pre-formed pairs.
So your last point, we are planning to condense. What are you guys planning? Like, what's the next step to actually do this?
Yes, we're measuring.
The next step is.
I'll mention that later for my outlook. And the second project for the transport, we'll measure it in the transport.
Yeah, how much time do we have for the committee? How long can you stick around?
I should be back in Allen Hall by 4.
Okay.
Same for me.
You want to just give the next one in about 5 minutes just to show the.
Yeah, this one's.
How many
This is a.
It's a lot of work. A lot of work, it's a lot of work.
So it's a short story for a lot of work.
Yeah, so trial motion for model layers in plan field. So the measure, we want to see transport, right? The new transport. So we start something simple. Firstly, when you deal with ohmic contact, you might have ohmic contact
Well,
either.
let me just set this up. The try-and experiment, but it's proving a principle that we could measure transport optically, which if it works, we could then apply to quaternions.
And we do see the triangle moves. So we are looking at the triangle applying a charge and it's moving. And how we know it move? We're looking at basically that basically dragged by the electric field, also diffused by itself, basically drag diffusion models. And you will see it moves by looking at PO. So this is the exciton, this is triangle. You can see at the field, the triangle, the center of triangles move a little bit higher than excitons because triangle is charged and exciton is not. So they have this displacement. But the fact that it's linear towards the field, we have measurements actually pretty linear. And we can calculate the mobility of triangles to be similar to literal values. So kind of, we do measure the mobility of triangle by purely optically way instead of just measure the currents.
So go back to the previous slide just to look at that a little bit more closely.
Yeah.
Okay, so I think you need to unpack figure C a little bit more for the audience.
Yes. So the x-axis is energy spectrum, as we mentioned before, is from the spectrometers. The y-axis is the position. So there will be bizarre to say why I have position here, because well, our spectrometer kind of they have a slit on it. So on the x-axis, they will convert into the energy spectrum by the wavelengths of the spectrometers. All it preserved is the y-axis, still belongs to the real image, the real space. So it's basically a hyperburst image with the x-axis to be the energy photon, the y-axis to be the real space position of this emission on the samples. So as you can see, if you make a slide here, the center of triangle and center of excitons are not in the same place with charge. And you can see this more clearly while we add in more charge. You can see here the center, we're tracking the center. It is different with different voltage. And you can look at it by eyes. One thing to know, we are applying some field. You can see the density is different. Sometimes trials brighter, and axons weaker, because when you apply the inclined field, they're also doping at the same time. So you are looking at sometimes axons trials getting brighter, getting dimmer, proving yes, we are applying a field, inclined field, but doping at the same time while we apply inclined field, you can see a displacement of the emission. Then what do you know by dragging the trial away? There's a proven saying, yes, we'll be able to now distinguish the motion of the trials, and will in the future try to distinguish the motion of materials.
So, I have a question about the setup.
Yeah.
So, did you pump in a small region of 2 micrometers? Or?
Yes, our pumping of very small area.
Oh, and so the idea is what is being pumped then are
Yes,
moving.
moving, yes, moving very small.
That's why you see a position difference in
Yes.
emission.
Yes,
Yeah, go to your drift diffusion equation here.
yes,
That was,
yes, one,
so
yes,
the drift term presumably is only for the tryons because the exciton's are neutral.
yes.
Oh,
So you can only see diffusion for both cases, but only drift for trial.
I see.
So you can use solving, consider a Gaussian package, you will seeing this, if you center, change, moving the center here by dT, there's it drifts away, if the center move away, they also have come broaden as well. So so in the future, we are also trying to do it for quaternion, and also we're also trying to see, since we know we have 2 layers of bilayer systems, and they all share the same charge. So we can actually drag it. You apply a dragging current on the 1 layers, you can drag the current on top layers. Someone already did it for interlayer exciton. For interlayer exciton, we have electron in 1 layer, hole in another layer, and their current are in different directions. The current here are in 2 different directions. But in our case, we drive 1 layer, I observe the 2nd layer, they should be the current same directions. So that nobody have seen before. We never have seen a drag effect for current happening in the same directions. This will be our next goal, which Daniel will take care of.
So which experiment is easier experimentally for quaternion, dragging or drifting?
Drifting, maybe, I'm not sure, but
The
probably
optical drift is probably easier, but
Easier.
harder for synchroconductivity with.
this one we did from city. We can see the direction of the coherence of the system. In addition, the transport property for coherence. If you see a coherent property of the transport, what's a non-linear behavior, you will see a reduce of the resistance. That can be a proven thing, when reaching some kind of the superconducting state. In my thesis, I have a chapter talking about 2D charge force and interactions. You might not be able to see a big drop, like 3D case. For 2D case, not all the quasi-condensed particle are contribute to superfluid. The superfluid fraction are only belong to a small portion of the condensation state. So you will not see a very big drop. How I say a slope of reducing the resistance. So this is also a improvement for showing this. You will see this happen on both states if they are condensing together. Yeah, so there are 2 own basically the conclusion. We try to get it quick. This is the conclusion of all these 4 projects. Starting with we fabricate the wide area samples, make it wide coupling all over the place.
So this is the general conclusions.
The
right?
general area.
Okay.
And then we go to we found recoupling to strong coupling for the quantum wells. Then we go to proving the quaternion. Then we move into the trial motion, which is our foundational step for measuring the transport properties of a quaternion itself. Yep, so basically that's all. And then the public list. Thank you. Yeah.
Okay, so we've already had questions on the earlier sections, but questions on the last couple sections.
No, go ahead. For the transport measurement,
Yes,
was it with a pulsed laser street camera setup? I missed it.
it's just a driving current. So it's no,
So it's all DC.
all DC.
Oh, that's nice. That's easier, right?
It's easier, right? Not that easier.
Oh.
That easier.
I see.
What is the typical binding energy for quaternion?
That's that we have this combination here. Go back to the calculation by the Bondrov. This one. I think this is a relative term to the excitons. It's only two trons. These are relative energy towards trons. I forget what's the transfer energy. So this you can read here.
Gray is the tron.
Yeah, gray is trion. So it's roughly 1.9 MeV. The trion is 1.3, right? I forget.
Again, those are the,
Those are the relative,
All relative to
relative to the exciton.
to the exciton.
Yeah,
So it should be, for example, the trion here is minus 2.2, so it should be 1.67.
No, I mean it relative to the exciton. That was my question.
Oh, yes, it's more relative toward the exciton.
Because, so my, I mean, okay, so this is not a negligible amount, but my follow-up question would be when you do the, what you said in your outlook, these dragging experiments, are you worried at all that, you know, by trying to drag it with the voltage or so, you're breaking up the quaternion?
Yes, that's something we do consider. It's tricky here. So like the order values in DC, but they still know that before not breaking the quaternion in the drag. We can also measure it by as Daniel trying to do. You can even measure the energy by the drag. You can say how much current you apply to destroy quaternion. It can give you
this basically puts a limit on the voltage or current that you can apply. Is there anything else to consider for that?
so, the drag effect.
No.
Yeah. Although it kind of is involved, yeah. I think I'm not saying
I know this will be, you will be doing it, but nevertheless.
Yes. But let me bring back to the into why it's so much. Yeah, so let me bring back to my drag effect. Yeah, firstly, when we do the drag effect, we are using we are moving them at the same direction. So if you apply voltage, say plus minus, moving in the same direction,
I see.
you will not destroy it. So
You
if
try to tune V and I
Yes.
against each other.
for the interaction, then we have like only if you only have this, if you apply this, you will destroy it. They move to two different directions.
Right.
Of our quaternions, you apply voltage instead of voltage on both layers, they will move in one direction. They actually distinguish us from all the people who are doing the interaction drag effects because they are having the currents on two different directions while we are looking at one direction. So the case doing that, we apply voltage on both here and here, and we will still see an increase of drag. So that means this is not our quaternion of interaction. They do in the same way, they will destroy the interaction, they will not see the drag growth.
Okay, thank you.
So how large is the quaternion? How large is the bound state?
How do you mean the
space or real estate, yeah. Should be order of the
It will be the order of epsilon, which is a point, which is 0.5 amps, no? Like a standard.
No, it's bigger than that.
So 1.5.
I thought they were like some nanometers.
No,
Yeah, it's actually about 1 nanometer, the size of the trion. So, and we in our previous publication we evaluate the size of the trion, and so the quaternion is roughly in bottom layer. It's a trion, and at the top you have an extra electron. So the size of the quaternion is the same as the size of the trion, and it would be 1 to 2 nanometers.
1 to 2 nanometers.
Yeah, for radius.
It seems
the size of the trion.
The quaternion just by external electric field, right? Plus, it's hard to accumulate enough energy difference within the size of the quaternion.
Yeah, but you can't.
There will be enough around.
But there will be
You're
other
right,
bonds.
that shouldn't be the first.
And also, you can tear it by applying different voltage. They go this way and this way. You can tear by the different.
Well, you're
direction.
not applying like 1 EV, 0.1 volt over 1 nanometer.
Yeah, but I'm not applying this.
So I think the biggest difference, or the biggest problem is going to be that this is never a pure quaternion gas. You also have indirect excitons and
Yeah,
other things around.
Yeah, that's a tricky thing.
And so you're looking for an additional effect besides those.
Besides, no, but again, you can tell the difference because again, we are dragging in one direction while the other. What is?
That's a touch.
I think it's just on screen, just swipe it back.
That screen is touch.
Oh, something. Oh, okay, but so this.
That's where the optical measurement actually has an advantage because you
Yeah.
can actually separate which one is which and what they're doing.
So we'll do both. We do kind of while but we measure the drag effect while we're also looking at the spectroscopy, looking at the movement of the drifts. So per se, both optical evidence and transport evidence can identify the transport coherence and tell the differences from the other interlayer or the other tectonic compounds. Yeah, this will be our next move, which will be Daniel for project.
If there's no more questions from the audience, we'll go to a closed session.
I'll quickly go to the restroom.
Okay.
We have three. Is that Nathan joining us eventually?
Nathan never joined. It was just me that's on there.
Okay.
Yeah.
Nathan joined eventually. I can save the recording and send it.
Can I ask you a question?
Yeah, sure.
Yes. So I looked at the thesis and I found some typos over there.
Oh,
And I
really?
would like you to, yeah. Just very
Only-
basic ones. So, for example, I can give you some spots where you need to correct it. It's general exciton picture. Let me show you this. The page.
You want to share screen? I
page.
can allow you to share screen. That means.
So in general, Igor, any typos you find, send them along and definitely.
Oh, okay. So just
we'll have
see
time to
it.
update it.
Yeah, I still.
It's an equation. It's the equation number 4. You
Okay,
have
you can
binding
share
energy
screen
with
now.
there and added kinetic energy. This is not supposed to be there. It's just the binding energy. Kinetic energy goes separately because your equation, showing your equation number 2, it is a relative coordinate equation. You have reduced mass over there, so you already removed the translational part out of this equation, and then you get the binding energy. It only should include the first term. That's the binding energy, and then a squared, k squared with 2m should not be there. You remove it from
I know.
there.
The kinetic one, you mean? Oh, okay, I remember. Okay, yeah, I recall now what you're talking about. The kinetic energy, right? Because for the x, the binding energy. I recall now. I said, yeah, I should know it
So
includes
this should not be there.
include the kinetic
Some
energy.
other typos as well. I can send them to me.
All right,
to
thank you.
So what are going to be next steps for this
Yeah,
session?
we have a
We're going to discuss.
close discussion. Yeah. I can
Uh-huh.
keep sharing the screen after this. Yep.
Okay, so at this point, questions on the thesis are also allowed in addition to questions on the talk. Igor, did you hear that? If you have
Yeah, so
questions-
my questions already, I already told you my questions. I have some typos over to report, and
Yeah.
they need to be
Yeah,
taken care of.
questions.
There is just formal correction that I would like to be implemented over there. Like
Sure.
this kinetic energy needs to be removed, and then there's also typos in figure captions at the beginning. And also, I would like you to mention Ritava paper directly in the list of references as well. I can send you this reference.
Sure. If you can send
You
me the
mentioned
correction.
Keldysh-Ritava potential. Keldysh-Ritava potential. Then you give only Keldysh papers there in the reference list. But this is actually Ritava's potential, and then Keldysh repeated that 10 years later. So
Yeah,
it's
okay.
better to cite them both.
Yeah, sure.
Now, also, I have here equation number 7. See, you write the
Let me
Kelder
bring
Schlegel
out my
potential
thesis.
here, then. Yeah, I'm talking about the thesis.
I know, just bring it out.
It's page 11.
Okay. Page 11.
Previous one.
Yeah, it's take a while for this room. Oh,
Yeah, here, down, yeah, one couple of lines down, Keldysh potential. Yeah, right here, number
This one.
7.
Yeah,
Equation number 7. So you have here what? You have R naught here, and then see the explanation that you're given there. H naught, Y naught as true and basic function. I don't think that this is a second kind. That it's a zero kind rather than second kind. This is
oh,
first.
yeah, it's zero order. Zeroth order. Yeah, yeah.
Zeroth order.
Yes,
Right.
yes.
And then you have chi2d, which is not present in the formula actually.
I have.
Chi2d it is inside of R naught. So you need to give the R naught expression here and then explain what chi2d is inside of R naught. That's the part of R naught.
Yeah, I'll add comment here of R0.
Yes, so this whole paragraph related to the description of the Kelder
Send me the email.
Yeah, I will. Sure. I'll send you the list of typos and corrections to be made. How much time do I have actually for to report those?
Until 3:45, but we have a couple other people in the room to ask questions as well.
Mm-hmm.
Yeah.
Yeah, I'm done.
Okay, we can come back to you. Let's give these guys a chance.
Yeah, so
Yes.
I would have a few comments about the thesis. I think most of them are too specific to talk about now, really. But I can maybe, so I send them to you by email too.
Okay.
But maybe let's just do one of them. I'm curious. This is on page 32.
32.
Equation 58.
Ooh, that's it. 58.
Mm-hmm. Right.
Yeah.
Oh, I guess your equation numbers changed.
Oh yeah, because I sent you a new version because we just was first know about that.
Okay, well,
which one?
which one does it look like here?
And none of those.
Is that the lower one?
The point a little lower, yeah. What? Little further. Yes, it's 66, I believe.
66, yes.
Yeah, 66, right? Oh, the whole equation changed. Huh, interesting. Because before you had an equation there that had a sum over matrices M sub J.
Yeah, the
M
image.
sub J is diagonal, and you get something that's non-diagonal in the end.
Yeah, so it should be something with both interface and the slab.
So something was missing there. Okay.
Yeah, already added.
Okay,
There should be interface and slab with something both interface and the slab transfer matrix.
Okay,
So
so this was
zero
already
fixed.
addressed then. Okay.
Yes, that's fixed. I think I sent you a new version of it.
Okay, good. Yeah. Let me then ask maybe one other question, which is not related to the thesis in particular, but generally, I mean, for instance, in your slides, I noticed there was at least one plot where you showed error bars. But in most plots you did not.
Yeah.
Yeah. So my question is kind of, so apparently if you have one plot that shows error bars, you had some way, at least for some quantities, to evaluate your precision, your uncertainties. But you don't show them in all the plots. Did you somehow, were you able to figure out that they are negligible, or what did you do with that?
So the reason the error bar is that for those pictures about all fittings. So when you extract the energy of the PL while fitting with a Lorentzian, that fitting creates you the errors.
Okay.
If you just plotting like intensity as total, it's just a directly outcome from the CCD camera.
Mm-hmm.
So there's no error except for the error from the experimental.
Yeah, experimental error. Okay.
So I also only I saw the error from the fitting error.
Yeah.
So
What about experimental errors then?
it's hard to tracking.
So it is a funny thing, but the convention in condensed matter is that unless otherwise stated, that the experimental uncertainty is just given by the scatter of the points. And it's usually, you don't plot that separately.
Yeah.
I'm aware of that.
They just like that convention, but.
So I only
but
plot
yet-
for the
But I'm
fitting.
still
When you're
curious to
fitting,
see.
you plot the errors of the fits.
Yes.
But if you're just plotting the data, it's typically not normal to put the instrumental resolution.
So that's why I only put the error bar for the fitting figures.
Part of it is just because if you want less error, you just integrate longer.
Yeah, that's true. If you're looking for integration longer, you will reduce the error bar into the.
Good. So that maybe brings us to the point. So how do you know when you took enough data?
How do I know it took enough data? You you can always take more data. You will stop and sample dice. In our case, our TM sample.
Well, okay, let me concretely go back to your presentation, because I had a question there. Go to the one where you were comparing the intensities of the 3 different encapsulation methods.
Oh, okay.
Um,
That's very early on.
Because I actually had a question about that. Yeah, right there.
Yeah.
Right there. Okay, so what I just said is that looking at this, you would say that the uncertainty is roughly that here for the instrumental.
Yeah,
Here is tiny.
tiny.
Here we can't tell because it's so small. But I have a question. Why, if this is so much more intense, does it have more uncertainty? Was there a different measurement time or something? Like, why is the one so much noisier than that one, even though it has more intensity?
Oh yeah, so that one have a less. No, so the thing is, they are all measured in the same life. Can
You need to plug in your computer.
you see it?
Yeah, it says your battery's about to die.
Oh. Yeah. So you can see it. So it's interesting. It's because of the GAN. Because that's a very charger. Oh, I forget to bring the charge. But I can't,
Well, just talk about it.
okay, so
Natural
again, so they are all controlled at the same. I divide them all by the same unit count and divide it all by the same integration times, but the gain is different. The gain of the camera is different. This one, because I'm taking the more integration time, the gain is lower. But you divide it, it become more noisier because the gain is low.
So you're saying those are the absolute intensities are comparable.
We can compare,
But
compared
the
to the,
gain and the measurement time was not the same.
yes.
And so
When you divide it,
effectively, you took many fewer counts for the yellow curve,
for them to make a match with the same integration times.
but then you multiplied it by that correction
Yes,
factor.
that's why we can compare them. Let's compare them in the same integration time, same saturation. But if you zoom it out, they become more zigzag because
So,
you can divide a signal.
so to answer your question, were he able to redo the experiment, I would say he should integrate longer on the yellow, right, to make it comparable to the blue.
Yeah, because it's very bright, so you integrate for the less time. Then but you need to compare apples to apples. You can't compare a long integration time with this image compared to the low.
But they were taken on different days and. so
Yes,
you didn't.
But if you can bring up your lasing kind of plot, you know, the pump power versus electron emission,
Which one?
anyone.
It's like the S curve. that you
S curve,
showed.
any S curve like this. Maybe it's not S curve. This one,
No,
the final S curve one.
Yeah, for instance, that one.
okay, yeah, that's fine. So there, you know, for instance, if I look at the leftmost dot,
Oh yeah.
right?
Yeah.
I could in principle say, oh, there's another threshold there.
Oh,
So
you saw the left.
You somehow concluded this is probably, you know, some measurement uncertainty that moves along. the
Look
line.
at my fitting, you can see very big uncertainty here.
Yeah, no, it's a good point.
Yeah, but that's just an uncertainty of the goodness of fit, right?
Yes.
But in some sense.
No, it's a good point. The error bars on the left curve would not be a bad idea, because you're saying that actually the low density ones, the uncertainty is getting pretty large.
Yes, so you can show my error bar, very large.
So you could actually just put like a square root and then error bar on.
Square, but yeah, we can put a square and error bar here, showing the intensity, because very low energy, your sample is very dim. So very high uncertainty because the signal is tuning. The
Right.
signal to noise ratio is very low.
But this would be, and maybe experts would of course know that immediately, but sometimes this would be useful to illustrate it.
Yeah, sure. Or
Right,
we
because
can
that-
add the arrow bar, this.
Because it's not only the question, if you have this broken line thing that you fit to it, of course I can see, okay, this is the best fit you get, right? But could it be something else, some different functional
We can do
pendants?
square and D. This is not the case.
Yeah, well, that's a good point, because the jump is only a factor of 2 in this case. And that factor of 2 is comparable to the uncertainty of high
Right.
density data.
Right,
So that's where putting error bars on the left one would actually be a good idea. And you didn't in the publication, but you can fix that in the thesis
Yes.
and put in an actual error.
But we can't, this one is from direct data from CCD camera, so we want the square and.
I would just take square root of n of the actual count numbers.
protein count numbers.
Yeah, I mean, this is just photon counting.
Yeah.
So it'll be 1 over square n, because the
Right.
lower photon count you have, you are less uncertain.
Well, it's square root of n over n.
Let's go over n, yes.
Okay.
So basically square n, 1 over square n, it's square n over n, so it's
Yeah.
square n over 1, 1 over square n.
Yeah.
Yeah, I'll do it for 1 over square n for each of them.
Yeah, or maybe even just some representative ones, so that it doesn't get too busy. You could just put it 4 or 5.
Yeah, maybe it's little bit, that's fine. Yeah, I can add some.
Yeah.
Yeah, I can add like for the lower one, middle one, the high one, I can add for each. By the square 1 over square. For the total count, you have uncertainty. With the more photon counting, you have less, more certain. With less photon counting, you will have more uncertainties.
Yeah, go ahead.
I have a theory question. So for the decay of quaternion into 2 electrons, so in the final state, does the 2 electrons also have spin 1? How is their energy depending on magnetic field? Do you have that analysis in your thesis?
So because of the spin one, they are all spin 1/2. So they are.
Together.
Go to the selection rules.
We can go to the. Go back.
Maybe in the thesis, you have this selection. rule.
Yeah, I have a selection rule. Yeah, or you can start with this because of
Well, that doesn't show where the recombination is. though.
yeah, I can go to thesis for the selection rules.
So if it looks.
Let me go back for the excitons selection rules. Let me bring it back.
There it is.
So because of their spin dependence,
There it is.
let me bring it. Let me share the screen. So I have a selection rule. I work it out for all the string structures. Your exciton need to stay in either of the values of k or k prime values for your excitons. So you are leaving them at that exciton.
Go down to the selection rule for the quaternion specifically.
For the that's at the end of chapters. Let me bring you to the. Yeah, it's getting slow. For relief.
Yeah.
Yeah. This is go up. I think in that we have for the. Yeah. Yeah, before that.
Yeah.
Yeah.
So that's the upper one, right?
Yes, upper one.
Okay.
So that's the wave function of
So wait, so you have a, this is the electron?
Yes, the electron.
Electron hole,
Black hole is this one.
leaving behind 2 in the same spin state? It's wrong.
No same spin state. They are the same.
Oh, wait.
Operating
This is,
spheres.
okay, here,
This is a spin one. This is a spin +1. So you will have your k and k prime value. They come together. You are leaving this both 2k -3. This is the negative case. So those are the exciton and conducting band. Those will disappear. So you are leaving you a spin -1, a spin +1, and this is a spin. This is a spin -3. Spin -3 + 1 is -2. Spin -2 is m equals 2. It's an orbit of
So
the orbital momentum.
so
It becomes 0.
the photon comes from the minus 1/2,
Sorry,
and the 3/2.
the 4 spins you have there.
So this
The
is all,
spin of the 4 electrons.
These two combine to give you a plus or minus, in this case, a +1
yes,
photon.
one photon.
So you're left with these behind.
This behind accounting with the orbit momentum. So remember, we are on the band. Electron spin are not random. They are coupled with orbit momentum. So when they are said to be most negative 3/2, the -3 plus 2. The 2 is coming from the orbit momentum. So why expand why electron is not like a spin 1/2 or a spin plus 1/2? Why I write it in the spin 3/2? Because we have the orbit momentum, which I solve exactly in the introduction part. So because I can't think orbit part. Like you count the total, counting the +2 from the orbit, the total is 0. So they don't contribute. The final state don't contribute to the.
But,
Okay.
his point was there is a Landau orbital energy of the final electrons that are.
They did not drift. They might move, but they will be linear. Like the total J.
So is there an analysis of the final state energy dependence on magnetic field?
I don't think it will be dependent on magnetic field because again, there's a exciton will be because they're fixed orbit. So they are.
So my question is this: so in the final state, you have 2 electrons with some net angular momentum and a spin angular momentum.
Yes.
So their energy will depend on magnetic field.
Yes.
Where is that dependence?
There will be.
So is that somewhere in your system?
Yes, I mentioned it in the sheet. So but this is gone. We're looking at 3/2, 2 minus 3/2, and those minus 3/2 plus the orbit momentum of the band is
Just
plus
charge.
on the charge plus. So because the electrons are not sitting nowhere, they're sitting on the orbit. If you plus the orbit, the total J plus in orbit is 0. The total J plus orbit 0. So the electron sitting on the conducting band actually at certain value will do not shift. And we're looking at the exact value because the values shift together. So if you look at one circular light, because we will examine at the one circular light, right? So we're looking at the emission of light from one certain values. Also looking at the exciton and certain values. So that exciton actually move with that. So the total energy, you will not see a shift of the exciton if you're looking at the right circular light. So right circular light.
Well, again, the photon energy is the difference between the initial energy and the final energy.
Yeah.
Yes.
Right? And so the quaternion presumably has a Landau orbital energy because it has charge.
It's charge, yes.
In addition to its binding energy, right? And then the final is 2 independent electrons, each in a Landau
Exactly.
orbit.
Yes.
And I would assume in Bondarov's theory, he took that into account.
Oh, you mean the minus the total energy of the.
Initial energy minus final energy.
Oh yeah,
So you have to take into account the effective masses and charges for the Landau orbital energy of the initial and final states.
I think this is down here. Oh, I think about in past.
So Bondarov's theory is not completely.
Yes. It was taken into account. Actually, I can hear what you're talking about.
But my point is, even taking account the spin of electron will not interface into it because we are thinking that we are minus drifting 1/2 of the. It will be still linear, no matter what. You're dealing with a linear drift shift by charge of itself.
Yeah.
So-
Why don't you let Bondarov comment here?
Yes, I'm here. Yes, I'm here.
About whether the
So
energy-
these 2 electrons in the final state, they're taken into account there in this theory. So
the orbital energy counterpart.
yeah, so the spin Hamiltonian comes out average over all orbital degrees of freedom. Only spin remains.